Here is another relatively easy problem in Putnam, but it is not the first question in the session. In fact, it is the third problem in the afternoon session in the 1965 competition. We are asked to prove that there are exactly 3 right-angled triangles whose sides are integers while the area is numerically equal to twice the perimeter. Since the problem is about right-angled triangles, we know that Pythagoras' theorem must be triggered. The key is we can pick any positive integers m and n, and we can generate Pythagorean triples using these 3 formulas.
3, 2, 1.
First, let's check the Pythagorean triple generated formulas are true. Starting from a squared plus b squared, we can rewrite them as m squared minus n squared all squared plus 2mn all squared. Expanding the squares on the right-hand side, we have m to the 4th power minus 2m squared n squared plus n to the 4th power plus 4m squared n squared. Continuing the calculations, we have m to the 4th plus 2m squared n squared plus n to the 4th power. Simple factorization will tell us that this is just m squared plus n squared all squared, which is c squared. Going back to the original problem, we're given that area equals to 2 times the perimeter. Using this labeling system, we can rewrite area as 1/2 times a times b, and the perimeter is just a plus b plus c. Now we're going to rewrite both sides of the equation using these formulas. On the left-hand side, we have 1/2 times m squared minus n squared times 2mn equals to 2 times m squared minus n squared plus 2mn plus m squared plus n squared. After some housekeeping, we can see that the left-hand side becomes m squared minus n squared times mn, and the right-hand side is 2 times 2m squared plus 2mn. Factoring a copy of 2m on the right-hand side, we have 4m times m plus n. Because of this m plus n on the right-hand side, together with the m squared minus n squared on the left-hand side of the equation, this triggered the usage of the difference of squares formula. Cancelling m plus n and also a copy of n on both sides of the equation, we are left with m minus n times n equals to 4. Since we are dealing with positive integers, there are only 3 possibilities to have a product equals to 4, and they are 1 times 4, 4 times 1, and 2 times 2. Tabulating these 3 possibilities, we can find out the corresponding Pythagorean triples. In the first case, when n equals to 4, we have m equals to 5, and a equals to m squared minus n squared, which is 9, b equals to 2mn, that will be 40, and c equals to m squared plus n squared, which is 41. I will leave the remaining 2 cases as a simple exercise, and the answer for the 3 triangles are shown here.